Okay, so let's get started. My name is Malavas, student of information technology and cybersecurity researcher. You can get some details about me on this website, just some stuff. I'm going to use the resources I used in my session at Null Meetup, which was on the same topic, preparing for battle x86 assembly. With that, here we have some references for learning some more about this topic. This is my favorite book called Hacking the Art of Exploitation by John Erickson. It covers some really great aspects of security, networking, programming, almost everything. You name it, there's thing in this book. Same goes with Shell Coder's Handbook, but it goes deeper into this stuff about assembly language, machine codes, kernel, Windows operating system, everything, and then how to develop that shell code for specific that. Then this is all. This is a premium uh, course by Security Tube. Let's dive deeper into assembly languages. This is my favorite. So for short detailed information, there is this video by Level Flow. You can do this or contact me on this GitHub and everything. So let's get started. Okay. So what is assembly language? It's a low-level programming language. Initially, when computers were developed, they were talking only in binary, and it was really hard to store some large data, information, and everything. So they started to store data in hex formats. If you guys know hex, which is like 0x, ABs, whatever, this stuff. Still, you can't use that to program stuff, right? It's hard. So computer scientists developed this low-level programming language, which uses mnemonics. We will learn into that, and it's completely library independent. Like you don't need any dependency or anything to develop this assembly program. It communicates directly with microprocessor. So consider this: if you have 32-bit processor, you developed one program, assembly program for 32-bit processor. Then if you try to run it in another architecture or anything like that, it won't run. Assembly language syntaxes are specific for each and every processor. They have some different syntax assembly. We will see into that. So let's see this. This is processor. It speaks only binary. Okay. If we want to program CPU in a way to carry out tasks we want it to do, we have to program it in binary, like 0, 1, 0, 0, 1. It's a tedious task. Who can talk in binary, right? See, humans, we can't speak in binary. So we need something like this. Assembly language. It was initial. So its syntaxes are like this: move, EX, EBX, translator, assembler, and linker. This combines to be combines to be a different set of softwares like program, which compiles and loads this program and converts this binary machine language, which our processor can understand, understand and carry out some different tasks. Okay. Let's see what are we working on. This is called mnemonics description. Okay, so I told you that there are hex based programming like 0x, ABCD, whatever. This is called opcode. Okay, and now this move, XOR, add, all these things, NOP, hold, are mnemonics. Mnemonics are some specific keywords of this programming language assembly, like move syntax copies EBX, EBF into this. Okay. First of all, these are this EBX, EBP. These are the registers of x86 architecture, which is 32-bit processor set. Okay, let's first see what are registers. Everyone has programmed, right? Programmed some time in your life, like C program, Java. You have seen that. You seen variables. Have you seen variables? So same goes with assembly. Here, but here we don't have variables to store temporary values and everything. We have registers. These are registers generalized in three. There are many, but three registers: general purpose, segment, control. These are the registers types. Okay. General purpose registers are EX, EBX, ESP, EBP. Accumulator register, base register, stack pointer, base pointer. We will see into that. Segment register doesn't matter much for our security purpose. But main important is control. Control type registers are most important for us, like EIP. It contains instructions like pointer. Every instruction is carried out in a line. Okay, let's say this practically. Okay, okay. Now say this. These are line. Just consider this. First instruction. It would be second, third, whatever. So when we first start running our assembly program, it would be start with this line. Okay, EIP, instruction pointers. It points to a specific instruction, where to start, where to execute. So initially it's start from one. So first instruction, which is global start, it would get executed. Okay, specific mnemonics and everything compiled, and then EIP is increased by one. Okay, so EIP new value is now 2. So it would be second instruction. Same. Okay, in a sequential manner. So if we know EIP, if we know the value of EIP, we would know which instruction is currently being executed. So this is the importance of EIP. If you want to manipulate binary, like exploit development stuff and everything, when we go deeper into that, we control the execution of that specific program. Like consider this: you have a program running, right? Which just prints your name as an alert box. So if you change pointer to that alert box to something like OpenCalc or everything, so after you still have that binary, your exe program, whatever, you can customize that to your own specific needs. It sounds dull, but still there are huge impacts for this. It's used to exploit softwares, bypass keys, license keys, bypass antivirus, malware development, kernel exploitation, everything. Mostly they are all about manipulating pointer, EIP. Let's see, general purpose registers. Okay, so here we are talking about 86 architecture, which is 32-bit, which has 32-bit registers. Okay, so it would contain size of 0 to 31, which is 32-bit storage. This is whole EAX. EAX means extended AX, accumulator, extended register. This is all extended. Now, if we consider, we don't want 32 bits. The detail information we want to store right now can be easily fitted into 16 bits. Consider that. Okay, so why would we need 15 to 31 storage? It's all useless. It would result into some bad characters and everything. We don't need to worry about that. But if we want to store or use only 0 to 16, we won't use EAX. We would just use AX. This is just the lower part of the register. Consider this. We are not going 15 to 31 and everything. It's useless for us for that specific task. So we are using AX. Okay, so consider this. Here we have used EAX. If you want to use AX, simply we will just do that AX. See, simple. Okay. So AX is now then divided into two parts, lower and upper. Okay. 0 to 7 are called AL, then 7 to 15 are called AH. To store same reason, same way. If you would think that 0 to 32 bit, if you use 32 bit to store our 7 bit, whatever, the rest of the size is useless. You would think that why would it matter? We have 1 TB, 12 TB of storages in our latest computers. Why would it matter? But when you are developing a shell code for specific purpose, the size of that shell code really matters. Okay, the smaller the size of shell code is, the more use you can make out of it. So that's why it's important. Same way, base register, BH, BL, BX, ECX, EDX, same way they all are divided. Now let's see about stack pointer. So you guys know about stack, right? It's like storing a heap. Like you are putting one notebook, then on that top of notebook you are putting another, then third, then okay, fourth, and going like that. So if you have five notebooks like this notebook on the lowest element is called base. Okay, stacks base. You get that? So if you want to know the address of base of this current stack we have, it would be EBP. EBP, extended base pointer, which points to the base of stack. Stack we are talking about, it would point to address of stack we are talking about. Same way, ESP, it's stack pointer, but not about base. It contains the top of that stack. So here we have divided in many parts, 1, 2, 3, 4, whatever. Here we have divided only two parts, ESP, SP, BP, EBP. Same way, ESI, EDI, we are not going to use currently. Say, see, EX, accumulator register. Sorry. It's generally used for storing operands and result data. Operands, okay, let's see what operand. So, see, here we have used MOV instruction. This is instruction, MOV. It's an instruction, EX, EBX, ECX. You guys know that it's a register, right? Here, 0x4. It's written in hexadecimal format, but it simply means 4. 0x4 means 4. So by this instruction, move EAX, 0x4. What are we doing? We are moving 4 into EAX. Okay, we are moving 4 into EAX. So we are assigning 4-bit value to EAX. Same way, 1 to EBX. You getting me? Okay. Let's see. So base register pointer to data, ECX, control registers, loop operation. So you guys know that we have used for loops, while loops, everything, right? So consider this. You are executing this program. Okay. Or okay, this would be some small part of a C program. Okay, this is a for loop. So initially value of I is 0, then it's always compared to an increase. Okay, same way if we are implementing a loop in assembly program, we need some control like see, ECX, control register. It just contains the control pointer. Like initially, if we are iterating for the first time, like initially I's value is 0, so control value for that would be 0. Okay, so if we step into new iteration of that for loop, so I's next value would be 1. Same way, ECX that contains information stack pointer register. EIP. EIP is not divided anything for some specific reasons. Now let's see about memory segments. Assembly program is divided into 3 segments: okay? Text, data, and BSS. Text just contains pure assembly instructions required for our program, like this. So this we define section by section dot text, right? So here we have specified dot text, which generally just means that we are defining text portion of our assembly program. Okay, and this initial instruction global underscore starts, it does nothing but just declares underscore start as a global variable. Okay, global variable means like it tells assembler to start execution from this only. So it would look for underscore start section and start executing instruction from that section only. So it would start executing in this section, text section. We are currently in every instruction like move, edx, init, whatever this is all in text. Okay. Now second section was data. We contain our data like strings, messages, and everything like that in our data section just for easy access. Okay, have a look. After text data text section is completed, we are defining data section. Here we have defined message. So see DB, which just means define byte hello world. Okay, so what would this instruction do? It would assign a string hello world to this variable called message. So and after this semicolon, whatever it is written is just a comment, like we do in every other programming language, same way. Okay, so here we call this variable message, right? So when we call this message, it would point to this hello world string. Okay, and that move that string to ECX register. Just bear with me. Okay, BSS contains all uninitialized global variables. The global variables who are not currently initialized with any values, not that important right now. So like global, it can be considered as that. Okay, see, like entry point of every program. If we are not defined any global variable, it would be this start text section, which print to screen. We have considered this hello world, so it would print to screen, then exit gracefully. So without doing any messing with our system, it would exit. And data section, that just contains hello world string, right? Now let's talk about memory. We have registers. We have many registers. Okay, we can store many informations we require. But consider this: we are not programming hello world. Okay, we are not programming hello world. We are programming big programs like we are developing a game. We are developing a big enterprise software. Registers are not that big, not that large to capable of storing every information we require to store. So that's where memory comes to play. What doesn't fit in registers lives in memory. So memory is accessed either with loads and stores at addresses as if it were a big array. It's like a big array. Push and pop operations are done in stack. It's just a heap or whatever you want to consider. Just consider this. Okay, this is the hierarchy of memory. Register files. Okay, this is the registers. These are very small in size, very small, but really fast. as they relies directly on our processor. Okay, so they can act really fast but really small. That's where comes L1 cache. You guys know about cache. I don't need to explain that. Cache. So it works as a cache for registers. Stores a little bit more information than register file. So 576 bytes, 64 KB. So it generally is 100 times bigger, but registers are 4 times faster than L1 cache. But still, 64 KB not enough. We need something more bigger, 300 times bigger, L2 cache, 20 MB, but still slow. So L1 cache is 1.5 times faster than L2 cache. Still 20 MB, we are very greedy, so we need something bigger than that. Then comes main memory, DDR, so 20,000 times bigger, but really slow. So L2 cache is faster twice than main memory. Remember this, or not, doesn't matter, just you need to absorb this. Okay, theory is hard, but we will move. So this is the most important part. Okay, if you are going anywhere in binary exploitation, reverse engineering, malware analysis, any important core fields of information security, you would need a strong grip on this data type storing in memory. There are two most common ways to store: little endian and big endian. We would see the difference between them, but let's see what are these first. Okay, so let's see. We have a string. We thought that we will be only talking about hexadecimal. So consider this string 0x, doesn't important for right now, 0x. Then 0, 1, 2, 3, 4, 5, 6, 7. Okay, we need to store this in this. Okay, so how would it be stored? In a big endian format, first this portion 0, 1 would be pushed. So 0, 1, then 2, 3. So 2, 3, then 4, 5, 4, 5, and 6, 7. Okay. Small in size and have very limited power consumption. Like they have very slow capability of power. Like mobile devices have ARM devices, ARM chip. They have very little capacity of storing battery. Like they need to be power efficient. So that's why big endian is used with them. But when we talk about Intel chipsets, we need performance. We need faster execution. We don't care about power. We have connected our computers to power outlet. We don't care about that. We just want best performance. That's why we use little endian format. Okay. So for little endian, we would first push last 2 bytes, not 7, 6, but we would push 6, 7. Okay. 6, 7 to first. Every cell can hold 2 bit. 6, 7, 4, 5, 2, 3, 0, 1. Okay, so this is how little endian is stored. If we want to read from this little endian, these are the addresses of each cell, right? By the way, 0x100, 0x101, 0x102, 0x103. If we want to read from this little endian, we would first read this 0, 1. Okay, then 2, 3, 4, 5, 6, 7. So we would retrieve back our string 0, 1, 2, 3, 4, 5, 6, 7. Okay, this would be more easier way to remember. Cafe, whatever. So simply explain big endian. It could be stored like this, little endian like this. I don't need to explain it. Explain this graph. Okay, you guys are smart. If you want to take a look. Okay, so control flow. You guys know if else statements, right? What does if else? Okay, let's see this. This is a simple if else statement. Consider if we don't have any if else or control instructions, it would be just go straight in this way, like 1 2 3 4. Simply it would execute in a simple manner in a sequence. But we don't want to do that. We want it to be dynamic. We want our computer to make decisions. So it would control control statements would do this. Check if A is greater than B, it would print hello, otherwise bye. Okay, this is a simple C statement for control. We want to do that in assembly. Jump. Here we have a jump instruction, but bear with me, jump doesn't take any parameter. Like if you tell jump to jump there, like okay, you guys know go to function in C, right? Go to function does nothing, but if you tell go to function to go to line 8, so it would be directly executing line 8. Same way, if you want jump function to go somewhere, you would just say jump 8. It won't execute anything which lies in between. It doesn't matter. So without anything like, okay, consider this just a simple program. So what it would be do, what it do, first it would execute this first instruction. It's not valid. I just made it up. It doesn't work. So just for explanation purposes, first it would execute move instruction, then it would go to jump instruction. Okay, jump to directly jump to ASD. So it would directly jump to this section only. It won't execute what lies before that. Okay, it doesn't matter what lies in between, what are the conditions, it doesn't matter, just execute. But JE, in contrary, it's jump if equal. Consider this snippet, move $5 ECX, it would be execute this ECX, it would move value 5 to ECX, same way move 5 to EDX. Then this is a new instruction, CMP. Compare instruction, it would just compare ECX and EDX. Then next is JE for JE. Okay, JE space function. JE would do that. It would check the previous statement, the previous instruction which was executed, and check for output. Like compare ECX, EDX. Okay, ECX and EDX are both same as 5, 5. So it would be EDX equal to ECX. So it would be JE equals to function. Like so, directly it would jump to this function. It would execute the code what lies beyond this. Okay, it won't do this. How it does that? How JE works? It has zero flag. Zero flag. Every instruction, every register can have flags. Okay. So what is zero flag? Consider this here. Compare instruction. What it would be do? What it do? ECX and EDX. It would just subtract ECX and EDX, like ECX minus EDX. So it would be 5 minus 5. What the output would be 0. Okay, 0. It has value of 0. So it would set 0 flag to 1. 0 flag would be 1. What it means? 1 means that it has 0 occurring. Okay, it would just say that there is a 0. So output of ECX and EDX is 0, and JE would take it as input. These are some basic instructions we encounter in while. INC increments the target operand by 1. If we have INC EAX, so it would just increment EAX by 1. Same way DEC. It would decrement target by 1. At destination source. At the source operand in the destination operand, storing the result in destination. Okay, consider this for this is the simple add instruction. Okay, So it would add it would add EBX into EAX and store the sum in EAX. Okay. Same way subtraction would happen. AND or XOR. You guys know this basic operations. LEA, it would load address of source into destination. Okay. There are layers. This is important to cover your basic understanding about computers. Level 0, bad metal. Metal means just our processor, chips, and everything. What lies above that is our operating system, Linux, Windows, FreeBSD, whatever you guys use. Linux not operating system, Unix operating system, which provides system libraries there. So Windows provides Bean API, Linux provides its own libraries. What it do that it provides libraries, functions, and everything to application. Like if a developer wants to develop an application, like if you want to develop this PDF reader software, PDF reader will use libraries provided by operating system. Operating system libraries it would use and generate some application level libraries, which is the topmost level. This is the bottom layer, syscall. So this is also important. In order to interact with the operating system, we have to use a system call. The operating system offers some services to application running on it. As I told you, operating system provides libraries and other functionality APIs to application running on it. These services are accessible using this system calls. Like if you want to open files, there is this call for that. If you want to map memory to somewhere, there is a call for that. Reading directory content, everything. There are a lot of syscall. You will never remember this. No one ever remembers all syscall, but they are easily available online if you just search. Linux syscall table for x86. Same way you can also file for Microsoft. Microsoft gives its own documentation. All these actions requires interaction with the hardware. Okay. If you want to do some processing, like consider this, you want to record some audio from the microphone. You need to interact with the microphone, headphone, whatever you are using. Hard drive, if you want to read memory. Everything is managed by operating system. Operating system just have drivers and everything required to access those stuff. Okay. So every possible Linux system call is enumerated. Like it has given number to it. Like if you want to use exit syscall, it has number 1, right for 4. How does system call work? Okay. System calls are also considered as a interrupt handler table, which handles all the interrupts. And this system call handler, it would execute all routines. So consider this. System calls are invoked by, like, used with INT. INT would just execute this 0x80, 0x80, INT 0x80. It would just execute the 0x80 system call. It would go to interrupt handler table, then syscall handler, then it would execute specific routine. Now, mode of invoking system calls. There are 2 ways you can invoke. INT 0x80, then SY center, but mostly INT is used. Invoking the, okay. So every syscall takes arguments. Like if you want to open a file, what would be the argument? What file to open? Okay. So you would specify that in this register. Syscall number would be in EX always. It would be in EX. Rest arguments would be there as well. So calling right. This is the right syscall. You find that in Linux manual man pages. I don't know if I have that. Install Java. So this is the manual write or write syscall manual. So it takes FD, standard out file descriptor, buffer and count. Okay, like ex would store syscall number. Okay, it would say which syscall we want to execute. If we want to execute write, we would store value 4 in our ex. Then fd would be 1 file descriptor. Then buffer, what we want to print. This is pointer to buffer. Okay, here we have buffer. Here we have buffer of hello world. So here we have a look. First we stored syscall number 4, which is for write in ex. Then file descriptor 1, file handler. Then buffer, which is message. But with that, we also need to provide length of the message. Here the length is 12. Hello world, whatever it is. And then int 0x80. Int 0x80 would just execute whatever register contain as a syscall, and then it would print hello world. Okay. Then we moved new value write, new syscall number 1. If you recall that, syscall for exit is 1. So we executed the meaning of program we require. Like we wanted to store messages, we wanted to print hello world. We printed it with this instruction, but we want to exit it gracefully without any memory issues and everything. Like, so we would execute syscall of exit. Syscall for exit is 1. This is argument required by exit, which is 5. Status code, it would be executed with status code 5. Then int 0x80. Okay, let's run this. How about that? So if you guys have ever compiled a C file, it uses a compiler like GCC or whatever you guys use nowadays. It's GCC or whatever. Same way, we need a compiler for assembly, which is NASM. And I have actually written a script here just to ease the. So we would compile according to this, or you would automate this also. But NASM ELF 32. Now let's see what does it mean. NASM, we are giving command to invoke compiler -f. What does it mean? What binary we want to it to compile as? ELF 32. There are many binary types like exe, bin, whatever. ELF. Linux defaultly use ELX. We are talking about x86 architecture, so ELF 32. The next argument will be hello world.asm. It's compiled. It would generate object file. Let's see what it is. Okay, see, hello world. It's an object file for hello world. NASM compiles our code and generates an object file. But we need to compile also the kernel level APIs. We talked about syscalls and everything. That operating system are gives our API libraries and everything required for our operation. So we need to load that specific library for our program. That's where load comes in. Currently, my system is 64-bit architecture. Okay, so if I use load this LD linker, it would just execute as a 64, but I don't want that. I want it to execute as 32-bit, like as we are talking about x86 architecture. So LDM. M is the switch we are using to give execute it as ELF I386. We are specifying what kind of processor type we need to execute this assembly. ELF binary type I386 is the x86 32-bit processor. Then our hello world dot o object file. Okay, it's loaded. Now you see, just like C, we have a dot out file generated. Okay, let's run it. Hello world. See here, I made some mistake. Yeah, initially in hello world, our hello world string was 13 characters. Okay, so I stored only 12. So it printed only 12. Hello world. This is garbage. Ignore that. So, we need to specify that. Okay. If you need to practice more on assembly and reversing, I would suggest this text file. And I would be sharing notes and everything. So you can download from here. It's a good community. Null. Don't forget to watch this video. It really cleans up your concepts. Okay. Well, anyways, thanks for watching. If you guys have any questions, just shoot them in comments. I'll be reading that. Feel free to ask questions as this topic is not that easy to teach and both understand in the first time. I'll be doing everything I can to clear your doubts. Otherwise, you can always reach me on my social media. Everything is provided on my website, I guess. And this is my Instagram ID. If anyone wants to ask. So I think we will conclude our session here. Okay. Thanks for being a good audience. Goodbye. Good luck,